Okay, just as a quick introduction, Xiao Zhang, welcome. Very excited to have you here. Xiao is a final year CS PhD student at the University of Chicago, working primarily with Michael Mayer, and his research focuses on computer vision, unsupervised representation learning, and generative models. And he's going to talk to us about designing scalable algorithms for representation learning, and also for complex image and video generation. So yeah, take it away.
All right, thank you so much for the introduction, and I'm very excited to share my research here. So yeah, so the title for this this presentation is called "On the Symbiosis of Generative Model and Representative Learning." So that's basically highlight my research. So I'm focusing on this kind of connections between generative models and representation learning, which kind of similarly orthogonal concept, but actually I will try to convince you that actually they're very important. They're kind of highly correlated. So in the past, arguably, we have this prosperity of the generative models. So we have, a state-of-art image generative model can generate high qualities and high fidelity images. On the right, also, we have this kind of state-of-art video generative model that can generate very complex thing, also like to follow this kind of real-world physics law. Yeah, those are pretty amazing progress. But despite there's so many progress, but most of generative models are kind of operating in this kind of two diagram. On the left is kind of autoregressive models, and on the right they are diffusion models. They are differed by how you crop the data, but they actually can be like understand in the lens of the noisy autoencoder. You crop the data and ask the network to estimate this, and those are basically represent this kind of mainstream architecture for generated models. So for my research, I'm particularly interested, in this kind of underlying mechanism of the generative model. So basically, what actually make this prediction happening? For example, in these autoregressive models, so we have this kind of orange box represent the input of the models, and we ask the model to guess what the pixel of this green box. So we know the answer here. It's some river and there's some stone on top. So, but actually, what make this happen? What is possible? So actually, this kind of content or input provide much richer information for the model to guess what the potential answer for this green box. So because see there's some river in the context, although there's some stone here, you can see those provide the possible hint to make the model to make the prediction correct. So that means in other way, if the model can to estimate correctly in the generated training, the model must understanding this kind of connection between context and target. So that means the model must understand those video structures. So this reasoning highlights one of these kind of key message wanted to deliver. So if the generative models can replicate or produce high quality images, preserve much of the richer real world video structures, it must understanding those concepts internally, maybe store as some representations. So it must understand this video representation internally. So in other thread, if this direction makes sense, then another question that's, can we improve the generative models by having better video representation? So basically, this kind of bidirectional connections basically characterize my research. So today I will like to present my four papers and grouping in two parts. The first part is talk about how should we improve the representation learning and how should we get the representation from the generative models. Okay, let's start from that. So let's firstly revisit this kind of self-supervised video representation learning. So we have the generative models, which have this kind of two corruption patterns, which either drop pixels or adding noise to the images. And then you have a model to reconstruct it. Those are generated pre-training. Another also very popular, also have the best state-of-art performance in most cases are contrast learning. So it operates differently than the generated training. So it take image and run some augmentation of the images and to train a CMS encoder with shared weight and to map images into some shared space and maximize their agreement. So the assumption in the contrast learning is that there's some shared features, some shared representation between these two crops. So and if the model can find them, and that means the model could reasoning about video structures. But compared to the generated model, it's have some more constrained setup because say if you take some images in outside, and it's very unlikely this kind of two crop will belong to the same category. But it works well for say the standard benchmark ImageNet because it has some bias of the object distribution. But this is state of art, state of art. But where is the general model in terms of the feature qualities? So here is a comparison. We'll compare between the MAE, one of the most representative general models, and the MoCo V3, which is also a very popular contrast learning method. And we do it on the standard ImageNet 1K benchmark. And we show the results using the k-nearest neighbor linear programming, which is kind of standard protocol for this representation learning benchmark. So you can see there's actually a huge gap, especially for the k-nearest neighbors. And there's also like substantial gap on linear programming, But the message here, the mass encoder general model learns something, but actually the performance is kind of far behind this kind of state-of-art control learning. So I want to investigate, what's happening and how should we further improve the model so that we can close the gap. Oh, sorry. Also, like, please feel free to interrupt me or raise a question during my presentations. Here, we try to visualize. So we want to understand what's going on. We want to first visualize what's the feature learned by the general model. So here we take the mass encoder, and to take this final output from the encoder, try to visualize by project the feature into some low-dimensional space. You can use PCA or TSNE, whatever. But the message here, you can visualize the features as images. So that means you can use a color similarity as a reflection of the feature similarity in the high-dimensional space. So from the images, you can see all this kind of, there's a girl also hold an umbrella. Also, there's some bush behind her. Those kind of things are kind of have the consistent green color in images. So that means the model think in the linear space. They're similar concept, but that's clearly wrong. That's not consistent with how humans understand the images. So maybe the model just using some trivial feature. For example, those three concepts actually they're spatially neighboring. So that means the model may be using these kind of pixel coordinates to cook up some features for that. Another thing we can find actually on the ground, there's a magenta color on the ground, and which is different, which is basically corresponding to the shadow of the ground, but that's kind of different from this ground without shadow. So that means in the feature, the model feel like this kind of shadow is kind of very important concept, but we know shadow is kind of low-level features. So that means by those two observations, it seems like the models tend to bias on this low-level feature with either this kind of pixel coordinates or this kind of shadows, but lacking this kind of concentration on the high-level semantic features. So that's the issue. But how should we solve this? So we take this kind of investigation on the kind of slightly different aspect. So we study the architectures. So specifically, we're checking the issue of the residual connections. So residual connections seem to be the golden standard after 2016 and have been like the key component for all the architecture, the transformer, the CNN, the UNet. You can find it in all the architecture design. So it allows the kind of the gradient efficient backpropagate in the very deep models. But actually, it's introduced kind of bias, which harms the representation learning in the general models. So the bias is that suppose you have some images, and this is the encoder of the general models, and then you expect some feature, from the general model to be, semantic, abstract. But because of these skip connections, so you can see this kind of shallow information, the pixels, so low-level details, they always a highway from input to the output. So that means whatever you get from the end of the encoder will have substantial portion of these low-level features. So that means that the model has to, inevitably to incorporate some of the low-level features in the end. So that's the issue. So now we identify a potential issue, but how should we solve this? So the straightforward answer, is that we just remove it. But actually, that's not a feasible solution because that will bring us back before the invention of the residual connection, ResNet. We will suffer from the gradient advantage problem, and we cannot really to train a bigger model, which is contradictory to the current practice of like scaling law. You really want to train a bigger model for general models. So, but let's just put that aside to see what actually benefit this feed-forward architecture can bring us. Actually, there's some analysis work to support that in the feed-forward network by removing these skip tensions. Actually, this network has a very nice low-rank bias. So that means output from this network will have some low-rank features, which is very nice, especially for computer vision, because for vision or for video data, the input usually very high dimension. There's so many pixels in the image in the videos. What we're interested in basically some low-rank feature, basically try to group pixels together. So what do you want actually some low-rank feature rather than the high-rank features? So for example, in the very toy model architecture, for example, in the MLP, just pure MLP. There are no activations, no residual connection, just pure MLP. So there's some very, very amazing analysis work from this Sanjeev Arora's group, which show that in the pure MLP architectures, the rank of the solution actually decrease over training time. So that means if you train longer, you guarantee the model will give you some low rank feature. Also, it have a much deeper models, then the rank of this solution will decrease much faster. So in another architecture, for example, the transformer, which we know they have this attention block, which have the following operation involving this software math over QK and V. This is very similar to the classic notion of the mean shift iterations, which and also another amazing analyzing work showed actually, if we remove this scale protection in the transformer block, it's guaranteed to give you the rank one structure, which also another low rank solutions. So that means in both network, we actually have very nice property, but how should we do? How should we actually to leverage this kind of benefit and to transfer to a different model? And our solution is very simple. We want the best of both. We want the residual connection. We also want this kind of low rank bias. So our solution is very simple. So we propose to decay the residual connections by introducing this alpha. Alpha is some layer specific constant value, which is which is between 1 and 0. So we also design some scheduler, so the alpha will decay over network depth. So in the beginning, for example, the alpha will become 1. So the first layer will be exactly the same as residual connection. As you go deeper, the alpha will decay. So it will gradually transit from the residual connection to the feed-forward network. So that means you can get the best of both. You can have, you can train very deep models, but also at the same time, because there's kind of decayed residual connections, you will guarantee to have the low rank feature at the end. And also another benefit of this design that we don't introduce any learnable parameters. It's just some predefined alpha, some constant. That's it. So if we apply this architecture to the MAE and to visualize again, so you can see the feature actually have very clear notion of semantic. For example, this bush and this girl, and also the umbrella that actually have different colors. So that means the model separated out in the little space. Also, if you check the ground, actually it's not sensitive to this shadow anymore. So that means it's kind of ignore this kind of low-level features, which is what we want. Okay, so go back to this benchmark. We see this qualitative improvement, and what about quantitative improvement? Actually, it's pretty substantial. You can see if we apply our method to MAE, just decay the residual connection, nothing else, we can see a significant improvement in terms of the decay nearest accuracy and linear probability accuracy on the image 1K. Any tiny improvement on image 1K is substantial. No mention, this huge improvement. Also, like we don't introduce any learnable parameter, just adding this decay scheduler. Okay, so we also apply our method to a more broad architectures. So for example, here we apply it to the MAE muscle encoder. We also try to apply it to diffusion models. So we compared our method, which is showing the blue bar, compared to the baseline, which is on the gray bar. So you can see we see a consistent improvements across all model design, and also because our design is kind of motivated by low rank feature, we actually compare the rank before and after our design. We see this kind of the output feature actually have lower rank, which is consistent with our assumption. And more interestingly, in the diffusion models, on image that 1K, high resolution, some 256 image generation tasks, we can see this kind of improvement of feature actually reflects as the improvements of the image quality, from 7 to 4 on image that 1K. That's kind of a huge improvement given, again, no parameters, no additional parameters added.
Yeah. Sorry, I just wanted to ask,
sure.
Does the MAE loss stay the same when you add this in, or is the model a bit worse at reconstruction when you do this?
Oh, so you mean the MAE reconstruction quality?
Yeah.
That's a very good question. So because muscle encoder usually have kind of extreme muscle ratio, say like I remember 75. So it cannot accurately reconstruct the pixel. So it gives you some blurry output sometimes. And we do some analysis to show, from this reconstruction, if it's blurry in the original design, also blurry in our design. So the reconstruction quality is basically the same. Yeah, but we want to show like more interest. I think for reconstruction, it's more interesting to check on the performance of diffusion models. So
yeah, I'm just curious if it's like reducing the modeling power to do this, but yeah, possibly it isn't. Yeah,
it seems like a regularization, just like how to weight decay dropout. It's kind of another like design of the regularizations. You cannot do a very heavy regulation. You have to like tune a little bit to make sure you have strike balance.
I had a question on exactly that point. How do you select those alphas?
Sure. So yeah, so we have a very simple decay scheduler. So we have linear decay from 1 to some alpha min. So what do we find? Actually, in most of the model, alpha min equal to 0.6 or 0.7 is sufficient. So we also like try to come up with some like principle to automatically select alpha min for different network depths. So the equation that we are taking this input, and because of the alpha, alpha L, alpha 1, so the contribution of the input actually decay over network depths. So for example, the total decay of the input is basically the product of all the alpha of the network depths. So if you have a you have deeper models, you basically want to control the alpha so that decay is slower. So the effective like this kind of the kind of product of alpha is the same. So we use this kind of the product of all the alpha as a constant as a way to select alpha min for different network depths.
So sorry, can you repeat that? What do you mean by the product of all the alphas?
So basically, we have a product from alpha 1 to alpha L. We want to make sure that is constant, because if you change the network depths, you will introduce you have different number of alpha. Because this alpha is per layer. If you have much deeper model, you have more alpha. You have much like heavy decaying factor. Okay. So that you want to make sure the overall decay factor remain constant.
Okay, so if you have a network of say 100 layers versus a network of 10 layers, the one that is deeper will have alphas that are closer to 1.
Alpha min closer to 0, because you want to decay much faster with fewer layers, but you want to decay slower, which we have more layers.
Yeah. Okay. I see.
Yeah. Okay. So yeah, we also try to apply our method across different model configurations. On the left, we try different channel. On the right, we try different model layers. So we can see the consistent improvements across all model configurations. So we want to use this method to to highlight the importance of thinking about the regulations in terms of the current hype of scaling law. As we build in bigger models, maybe it's also more important to consider how should we leverage this kind of bigger model to do more. This regulation is one way, and this kind of maybe is kind of missed in the current community, but also we actually show it has much more potential to further improve both representation learning and also the generation quality. Okay, so if there are no further questions, I'll move to the next paper. Okay, cool. So yeah, so in the previous paper, we talked about how to improve the general representation learning in the general models. But actually, there's another more severe issue for generated representation learning. So suppose say we have a diffusion model, it learns good features, but because the diffusion model has the kind of forward-backward noising chain, which in the forward path we gradually add noise to the images, and backward we have some network try to take noisy images and try to as a clean version of it. So if you think about this entire diffusion chain at different noise level, for example, at a lower noise level, the diffusion model just needs to to understand some low level, some corners, some edges, some texture to accomplish the denoising task. But if you move to some high level regions, some high noise level regions, the model has to reason about the global structures. They have to reason about high level features to accomplish the task. So that means throughout the entire diffusion chain, actually the model will have leverage or to learn a different features at different noise level. So that means for the feature, actually it's kind of distributed across the entire noisy chains, which is make this kind of feature inference or feature extraction much harder than the standard contrastive learning, which have encoder always take the clean image as input. So here we need to deal with a model that take different images as input to get feature. This is kind of a very challenging problem, and to make the problem even harder. So in diffusion model or in any generative models, what's kind of the common assumption that the middle block of the general model, you already encode some high-level feature, and the 2N, the input or the output, you already encode some mid-level, low-level features. So that means inside the general model, they also kind of distribute the notion of distributed features. So this kind of two phenomena make this kind of feature extraction for the diffusion model much harder. So to solve this problem, we propose a efficient clustering algorithm to project this kind of distributed feature into some consistent low-dimensional feature, so that you can easily interpret the model behavior. Also, you can directly use this kind of low-dimensional feature for downstream applications. So our method is inspired by this classic notion of the spectral clustering, but I won't go to details of that. But it's a graph clustering method which try to represent data as affinity matrices. So say you have images with n pixels, then you can construct some affinity matrices using pixel as feature, compute dot product, compute feature similarity between every pair of the pixels, so that you get n by n matrices. And also you can get this, the row sum of the affinity matrices, that will be the degree matrices. So basically from data, you get A and D, then you can construct these random walk matrices, which are D inverse A. You have the matrices, you can solve some eigenproblem. And the solution of this, the eigenvector, if you solve the leading K eigenvector, you can use it as a very nice low-dimensional representation of the data. And then you can do, say, if you want to get segmentation, you just run k-mean cluster on that. You get pretty good segmentations. This is kind of dominant method before the deep learning, which the spectral clustering will give you very good features. And also there's some recent work trying to apply. Because we have a neural network, we have better features, can replace this kind of conventional handcrafted low-level features with deep features, so we can have a better affinity matrices, because that's where the input for the spectral clustering method. So the idea that, say we have some models, say we have some transformer, we can take the query key and value from that, and we can say using some heuristic, for example, if that's an encoder, we can take the last layer of the transformer and use the query and key from the last layer to construct the affinity matrices. Then you can plug in this formula and to solve the eigenproblem, and say you can visualize the top 3 of the eigenvector as images. So that will give the sense of like what's kind of the feature learned in the models, which is okay. But this approach cannot be working with the diffusion model with the aforementioned distributed features, because now we don't have a single A. We actually have set of A. They could be sampled from different noise level. They could sample from different layers. We have a set of A. Then you want to find a U, the low-dimensional embedding, that can represent the entire A. So that's a very challenging problem. And because in the classic in the previous literature, there's some work trying to solve this problem, but try to construct a very huge A by putting all this kind of this A1 to AM in the diagonal and solve the big A, which is obviously infeasible and also cannot be scalable in this kind of modern architectures. So actually, our design is kind of like try to design some efficient optimization procedure to solve this problem. So our motivation is by viewing this kind of the classic spectral clustering from this eigenproblem to the optimization problem. So here on the left, it's still like this spectral clustering with the trying to solve eigenvector for the random walk matrices, but it has some very nice property. For example, if the data has k separate clusters, and so the solution, the eigenvalue, is guaranteed to have at least k eigenvalues. They're all 1, and all this eigenvalue for the random walk matrix is actually bounded between 0 and 1. So, sorry, is there any questions? Okay, good. So yeah, we can view as the optimization problem. We are, we still do the same thing, but we are trying to solve the eigenvector U. That's tried, this term will be some approximation of the eigenvalue. want to maximize the eigenvalue. In the best case, if we can find k of u such that it can produce an eigenvalue become 1, then we find u that's separate the data into k separate cluster, then we're done. Also, we have some additional regularization to make sure the u are also normal. Those are the same. They're nothing changed. We just change the problem from eigenproblem to the optimization format. But this optimization format offers some extra benefit. So that means we can actually to solve the optimization problem by sampling over set of A. The set of A actually all the collections of these potential feature sources, and we can solve the U by taking this kind of mini batch optimization, where each mini batch basically you sample a small set of A, which is easy to compute. Then because A could come from different resolution, A could come from lower feature with high resolution, or it could from like bottleneck with lower resolution. So you need some additional resampling operator to align the solution U with the incoming feature sources. You have the G. So that's it. We just make the optimization to be like mini batch version of this original spectral clustering. But this will offer very nice property. For example, we can now to solve the spectral clustering best sample A. So we can sample the A from different noise level. Also you can try different noise as well, and then you can sample different layer. Maybe the network has 100 layer, and each time you can just sample a 10 or 5 layer that can best fit for your memory. Then you can solve this problem by iterative over this sample, and to solve you can update U by several iterations, and then you can after converge you get the U which is have much better structure than the one that's just pick the best version, because now the U actually had a feature for all this level, and also you can see it preserves much of the high frequency structure, also like to maintain this kind of semantic contrast. This is much better representation than the previous version. Here is the more real addition. So here we are applying the stable diffusion, and to apply our optimization method. So during the optimization, there are no language, no label whatsoever. It's just pure optimization, express optimizations. So you can see this U basically preserve all the details, and also like how to preserve the semantic cluster. And if we apply this simple k-mean cluster, you can get very high quality segmentation from that. Okay. Also, like another nice property of our method is actually its benefit from this kind of nice property of the eigenproblem. So eigenvector, we know actually it's have some like natural hierarchical layout which is ranked by the eigenvalue. So we can also show our solution also preserve a similar property. So for example, this eigenvector with higher eigenvalue, they tend to focus on the high level, the global structures, while the eigenvector with lower eigenvalue, they're basically give you some very detailed object level representations. This kind of give you a very nice answerized hierarchical representation of the images. To further show the benefit, because we are doing the mini batch optimizations, we can actually to show our method can scale with large data set. For example, we have an image set, say have 1,000 or 10,000 images, and we try to build a graph connect between every pair of pixels of every pair of images. So if you have very huge graph, then the graph is huge. It is very intimidating. But because our method doing this kind of mini batch optimizations, so at each time we can just optimize a subgraph. We can sample a subgraph and to solve the U. So U is still like all the pixels of all images, but every time we only optimize a sub mini batch, so that after several iterations we can get some approximate global solution by projecting the features into some consistent global consistent low dimensional features to view some like the pattern of the features. So the application of this is that we can get answer-based segmentation for the entire data set, and also we can try to leverage as some like model analyst tool to prop different feature property. For example, we can say feed different feature. We can feed we can construct a feed matrix from the query and key. We can also we also construct the feed matrix from the value to by visualizing and checking their difference, we can understand what the features encoded by those representations. Actually, it's kind of very interesting that we find if we apply a method to the value graph, the feature is more like semantic. It's kind of similar to the semantic grouping. if we apply our method to the graph constructed from the query key, it have very strong spatial bias. For example, you can see all this embedding, the left part have the kind of consistent green color, and all this part on the right have the magenta color. So that means the models internally, the transformer architecture internally come up with this kind of separation, different computation strategy to process this recognition and the spatial reasoning task, which is very similar as how human have this kind of two orthogonal regions, which we call what and where pathway to process different spatial and semantic understanding tasks. This kind of computation strategy is automatically picked up by the model. So we don't introduce any bias. It's unconstrained. The model can do whatever it wants, but it just happened to convert to a similar structure as how human brain processes the informations. Because R2 we can have this understanding. It's kind of very interesting finding from our analysis. So we can further to extend our method to video, because our method can process the entire data set. So we can also replace the data set with some video frame, so we can get this kind of temporal consistent embedding. Also we can also show this kind of hierarchical embedding. You can see from here there's some line, which is also the right part is basically lower eigenvector with lower eigenvalue. So basically they focus more finding grain, and left and middle is focused on the high level. So you can see that we can get this kind of temporal consistent representation, also this kind of nice unsupervised hierarchical representation for free. Okay, I will quick stop here too, just in case anyone would leave a comment or questions. Oh, okay. So if there are no question, let's move forward. Okay, so in the first chapter, I talk about how should we improve the representation from the general model, and how should we build some efficient way to extract the representation from this distributed representation of the general models. So in the second part, I will talk about how should we do the other side of this arrow. So how should we leverage some strong video representation to improve the generation quality of the models. So in the diffusion models, so sorry, is there any question? Okay, cool. So in the diffusion models, so we're using a very simple toy case to illustrate the behavior of diffusion models. So say we have a 2 point in the 1D space, just 2 point x0 and x1, and x-axis indicates the noise level. So from left, that means there's no noise to add to data. And as we move from left to right, we gradually add noise. So you can see that kind of support starting from this kind of 2 point and to this to spread out to the more space, which end up with some Gaussian prior. So the diffusion model basically take a point on the noisy path and try to guess what the clean data is. So because of the topology structure of the point, for example, if we take the orange point here as input to diffusion models, and to ask it what the clean data is, because based on topology, it has 50 chance it come from x0. It has another 50 chance come from x1. So the optimal solution enters L2 distance, because we already trained diffusion model as L2 distance as to estimate the noise or estimating the data. So the optimal solution basically is average of the solution. So the best guess is basically here, is in the middle. But if you take another point, say a red point, because of topology structures, it's basically 100% is coming from this point x1. So that means even this red and orange point, they basically have a similar noise level, but because they're topology structures, they have different answers. So that's basically we are trying to use a toy example to show this kind of average behavior of the diffusion model, also the kind of importance of the data structures, and in terms of impacting the final denoising solutions. So this is fine for a 1D case, but what about for actual images? Because that's what we're most interested in. So say, we have a set of images, and we are we add some noise, have some noisy images, and we take diffusion model, try to guess what the clean is. Because of our analysis, at very high noise level, because the model cannot guess what the clean image it is, so the best guess is basically average set of possible outcome, which leads to this kind of weird average like images, which is, it doesn't make sense. This is not real images, because for images, they are not defined on pixel-wise average. Sorry. So that means they're in the certain part of the diffusion chain, the output doesn't make sense like semantically. Because of this space is not defined for averaging. Okay, now people say like, we're not doing this kind of diffusion on pixel space. We are doing the latent diffusion. We have weight space to which, hopefully can better to elevate the problem, but actually it's not. So say we are doing some analysis in the weight space. So what do we do here? We take the input images on left and try to reason about the nearest neighbor. So we can see all the neighbors actually have the consistent texture pattern as the input, but they actually doesn't have the consistent semantic meaning. So that means if you run the diffusion model in the weight space, it will still do the averaging. And also this averaging is because it's averaging is on the, say, a texture space. So it's still like averaging doesn't make sense. So to solve this, we want to find some space where, of course, it has to averaging because we're still running with the diffusion framework. Averaging is inevitable, but we want to find some space. The averaging makes much more sense. So that means, for example, we can do some like diffusion in the spanning space directly. Say, we can use, say, a cliff features or dino feature, some model give you very strong video encoder, and we'll try to run diffusion model in that space directly. So that means if you do average, it will give you this kind of consistent averaging pattern, which is kind of more meaningful than this kind of like previous weight space or pixel space. So to summary, so compared to the standard diffusion chain, which is showing on the left, have this kind of scale space diffusion chain, we more prefer this kind of chain on the right, which have following some certain semantic paths, which may be more consistent with how human perceive or how human draw the figures, and we want to follow this path to generate images. So to build a model for this purpose, so what do? We first construct this kind of semantical hierarchy target for general models. So what we do is a very simple operations. So we take image, say here we take image, and we split them into different patch, not overlap patch. For example, here we divide into 2x2 patch, and we send each patch to this video encoder independently. So say we have 2x2 patch. What do we get from that? It's 2x2 feature vector. And say then we can vary the patch size so that we can construct this kind of hierarchical semantic tree. Where at the top, we just send the entire images as a single patch. So we get a vector that corresponds to the entire scene. And in the middle, we get the representation for where each part of the representation focus on this kind of each part of the images. So basically we move from this abstract from the top to the middle of representation. Then we can keep doing that by shrinking the patch size where in the end we get the pixels. So from these operations, we construct this kind of hierarchical semantic trees. And we want to train a diffusion model following this path. So our solution is also very straightforward. So we deploy a diffusion model at each level. So for example, at the top, we have diffusion model try to directly generate a vector, a very low dimensional vector. Then we have a second level diffusion models that condition on the high level features and try to generate this kind of mid level features. And we keep going to condition to both high level and mid level to generate the pixels. Through this, we're still using this. We're still using the diffusion framework, but we are repurposing this generation path from the scale space diffusion to the semantic space diffusion. So which is more like consistent with how human perceive the world. Also like because it's operating in some semantic space, the averaging effect is also like it's kind of has defined property. Also, it's more meaningful. Yeah, this is our pipeline. And in terms of the performance, because we want to show actually that's have a substantial improvement in the generation qualities. So here we're comparing our method with respect to some like state-of-the-art huge models. So here we are highlighting this kind of the efficiency of our model so that we compare our models with others using the size of the dot to represent the flops. So basically, the bigger the dot is, the more heavy compute it leverage. For example, this DIT XL SL2 we're comparing with they have roughly over 100 G-flops, but our methods, because our design allows some efficient generations, we only need a quarter of the total flops. So we have much smaller dots. But compared to this baseline, this blue dots have more compute, 4 times more compute. But our method, this green dots, have substantial improvement in terms of FID, which is showing on the y-axis, and also in terms of training iteration has much faster convergence. So another comparison to this is that the RAPA. So this is kind of recent state of art, try to augment the generative model training with actual objective to align the features with some pre-trained visual encoder. We show our method still on the small green dots actually has a better performance than this. Also, because we are using much smaller models. Another more interesting comparison that this red dots is running in unconditional generations. This is a much harder task for image than 1K because there's 1,000 category. We don't tell the model what class it is, so the model has to to fit for the entire structure distribution to have a better generation quality. So actually, our unconditional models, with much fewer flops, actually outperform this RAPA augmented, bigger models. Also they use the condition all the time. So that means that's highlight this kind of effectiveness of this kind of redesigning of the diffusion model to run in the spanning space. So another point I want to highlight is on this more challenging task, the task to image generations. So we compare our method, which only a very shallow model would just have 0.2 billion parameters, 200 million parameters, but also training with much fewer data. We show our method outperforming the bigger model, which has 7 billion parameters, and also much more data. We also have a better FID. So that means we want to use those results to highlight the importance of feature learning or this kind of real representations in the process of general model. Okay, and recently, sorry.
Yeah, could I ask you a quick question?
Please, please.
At inference time, then, do you have essentially diffusion happening at all the 3 different stages of your pipeline?
Yes.
Where you first diffuse into the high-level features and the sort of patchified features, and then further on?
Yes. Yes.
I see. So it's a long. What's your inference time cost then?
Yeah.
Are you tripling your inference time?
Yes, that's a very good question. So the answer is the actual overhead is very minimal because the space on the top level is just one vector. It's very small space compared to this the token size in the actual image space. So because we are working in this kind of reduced space, so this actual compute flops is very limited. So I can give you some ideas of what's the cost. So here we are benchmarking the model at different hierarchical level. So L equals 2 from 2 level to 5 levels. X-axis indicate the G flops of the entire generation pipeline. If at 5 level, this 34 indicate this total flop for the all 5 level generations. So you can see by increasing the level, we are not actually introducing much of computing flops. Because this kind of after step are usually in the very low dimensional space, and this computing is very efficient. Does that answer your question?
Right. So the baseline model you're comparing here is a much larger diffusion model, right?
Yes. Yeah. For fair comparison, we try to expand their capacity so that we can match the flops.
Okay.
Yeah. Thank you.
Does that hold true for wall clock time as well? Because I imagine you have many more recurrent decoding steps in your method.
Yeah. Oh well, I think I want to highlight the change of space, because if you still running more inference time, it's still operating in the original space. Arguably, that will improve the performance a little bit. But I think we can also apply the similar thing in our model design. We can still try to allow more inference step. But we want to show actually at the same inference step we have much better quality. Okay.
Thanks.
Thank you. Okay. Yeah. So recently we also tried to extend this idea to video generative models. This is just submitted to NERPS 2025. I hope everything goes well. But yeah, so the idea is that I want to extend the hierarchy to both spatial and temporal, and so that we can have much more stable general models. So here we're showing on the application to emulate this kind of very chaotic 2D Navier-Stokes system with very high real number. That means it's a very chaotic system. So we are just having a very simple autoregressive model. You just take the previous frame, estimate the next frame. There's no diffusion at all. But we can show our method can actually it's our autoregressive model, but it can actually generate the frame infinitely. So we show our method, on this 512 resolutions, it can stably generate these predictions from to 100 step, even to 10,000 step, a very crazy setup for this problem. So we show the benefit of kind of redesigning this generation models in different space actually have much more benefit for either visual model, image models, or this kind of video models.
Wait, so what does this model look like if it's autoregressive, or is it just a hierarchical autoregressive model?
Yeah, it's kind of more like tricky than hierarchy. So we have to define the hierarchy in this temporal spatial space. That actually are innovations. So how to define this hierarchical patterns in this video data? Yeah, but you're right. Yeah, in the high level, it's a hierarchical model. It's a hierarchical deterministic autoregressive model. Okay. Thanks for the questions. So yeah, if there are no further questions, I'll move to the. Hopefully, I have time. Okay, I'll try to speed up. Okay, so the final, the last chapter is about how to leverage this representative design for a specific vision task. For example, here we are focusing on this kind of image intrinsic decompositions. So image decomposition is kind of very classic vision task, which basically to decompose input images into two components. One's called albedo, which essentially represents this color or texture of the object. And also another piece is called shading, which indicates kind of the reflections between lighting and the word geometric. Essentially, this is a very challenging task because in the real world there's so many lighting patterns, there's so many different surfaces have different property. So for example, on the left and the right, they're representing a kind of very reflecting surface. On the right, that's indicating kind of low lighting conditions. So if you try to solve this using some supervised method, the annotation would be extremely hard, even harder than segmentation, because here you really want to annotate the intrinsic color for each pixels. Even human, we don't have the consistent answer. So that means to solve this problem, people usually do this two-line work. One's called using the pure fire optimization. So basically, they frame the problem as the kind of optimization problem. Want to solve two pieces with some assumption onto each piece individually. For example, for the albedo, they already have this kind of piecewise constant. On the shading, they have this kind of spatial smoothness and prior. But this cannot handle this kind of very complex thing. Also, it requires some semantic understanding of the images. Another line of work is using the pure CG rendered images. But because of gap of this kind of render quality and real world, it cannot really to provide satisfying models if you try to deploy this to the real world. So what we want is to have some enterprise method, because annotation is very hard, and also directly train on the real images and to solve this kind of image intrinsic problem. So our design is actually very simple CMS autoencoder. So we assume we have the data collection from this kind of pair setup where we have the different lighting for the same thing. Those two images they're from same thing but different lighting. So we have some encoder try to split the images into two pieces. One is called global, which one is the abstract global vector, try to represent the light. The other is try to have some dense spatial representation, try to represent the scene layout to do this kind of to represent this intrinsic representations. So what do? We try to design some decoder that take the lighting from one images and take the intrinsic from other images, try to recompose images with some physical constraint, because we know this kind of intrinsic property should not be changing with light. So we have some laws to say, this intrinsic feature should be the same. And also, this if you combine these two things together, we will get images. So we also have another structure regulation for the low dimensional vector, because we are trying to use this low dimensional vector to represent light. So the effect of light onto the images, it should be very minimal. Also, like should be globally smooth. So we implement such regulation into this what we call constraint scale shift. So scale shift is kind of is a kind of common trick in all the diffusion model, try to interact between time embedding and also this feature map. So we take that setup where the L will basically a low dimensional vector and try to have them some like scale shift interaction with the high dimensional feature map. But we regularize the impact of L with some alpha. The alpha, because we have 10-edge, 10-edge basically map this activation between -1 and 1. If we have alpha, so the whole activation will be limited to between this minus alpha and alpha. In practice, we set alpha to be very, very small value. So the interactions from the L to the images is kind of limited. So that we have this kind of physical inspired constraint, hoping that this feature vector will capture the desired extrinsic, intrinsic properties by just reconstructing the images. So we actually show our method have very strong generalization ability, because we are training with this kind of constraint setup where we always assume the input images have from the same scene. But actually in the test time, we can actually show our model can do zero-shot relighting. For example, we can take one images to extract their lighting vector from the encoder, and we then extract the intrinsic feature from the different images. We compose them into render images. Actually, you can see it's correctly transfer the lighting pattern and also preserve much of the details, especially on the shining ball. You can see that's basically give the reflection of the environment map. So it's extremely hard to preserve this kind of details, so also like transfer light. But our method doing a very good job, especially on the zero-shot setup. So another very interesting property is that we can directly send the intrinsic feature to decoder, so there's no extra lighting. So that's the decoder will directly give you the albedo-like images. Even though doing training, it never been trained with any albedo images, but the model surprisingly gave you this albedo estimations. So in some standard benchmark, we compare our method, ours, with this kind of state-of-art regression-based methods, which is training on this CG label, the computer graphic generate images, and train a regression method. So we show our method actually have much better quality than this state-of-art regression method. Also, we have the variation of our estimated beta. Basically, we vary the lighting pattern on the input images and show our albedo animation has much more consistent with respect to this lighting change. So that indicates kind of the strong qualities of our estimated albedo. Okay, I will conclude my paper presentation here, just in case any questions. Please.
Yeah, I'm curious about the smoothness multiplicative factor. It's 1 plus alpha 10H.
Yes.
Where is that formulation coming from? And is your MLP turning your low dimensional L vector into some high dimensional space?
Yes.
That matches F's channels?
Yes. Yes.
Okay, so you're essentially multiplying across all the height and width with the same.
Yeah, it will spectral broadcast to all the spatial location of the F, but with its constrained range.
And why is this the right formulation for it?
So we just want to limit the information from L, because L, because you want some high dimensional L, because otherwise if you make L too low, very low dimension, the optimization will suffer. So you want to train with some L, but you want to regularize L so that you want to decompose information from extrinsic to intrinsic. Because if you don't do that, so even though you have some vector, but that vector could potentially to leak the information of the scene structures onto the decoder, so you don't have a perfect decomposition. You want to limit the information to encourage this kind of separation, because what you want is not just reconstruct images. You want to also like have this nice physical property for downstream applications.
Got it, I see. And so you had to construct this data set specifically for this purpose.
Right? We need to pair images, but that's kind of a less constrained setup, because you can have a camera just changing the lighting pattern. That's very easy to calibrate.
Mm-hmm. What other intrinsics can you sort of extract using this method? Lighting has this really nice smoothing property across your entire spatial region.
Yes.
Are there other intrinsics?
Other intrinsic? You mean extrinsic or intrinsic?
other sort of intrinsics? Are there other intrinsics you can learn using this formulation?
I see. So here in this paper, we are just primarily focusing on this albedo estimation and relighting task. But I think another interesting problem would be to learn a material specific lighting pattern, because different material have different reflectant configuration. So I think to have that understanding will also it's kind of very nice, interesting application. But we are not touching that in this paper.
Okay.
Yeah. Thank you. Okay. I think we are. Yeah. Sorry. Maybe you're running late. Okay. So yeah. To conclude, so this is a future. The slides for talking about my the research I want to do in the future. So yeah, I want to spend some time, because my focus is on representation learning. So I would like to. I'm also interested in learning the representation in the multimodal system, especially how to do the interaction between visual data and the language data to have a better representation, because that's kind of essential for all this kind of current multimodal system. So also I want to further study this kind of effect of row rank representation, because we from the Decayed residual connection paper, we show actually that helps a lot in both representation learning and generation quality. So I want to further explore other choices of on the regulation technique, also try to apply to different model. For example, want to apply to say language model, also this kind of visual language model. See, can that effectively improve the model, improve performance also for this video general models. So the third part I want to pursue is that want to have some models that have explicit learnable latent variable, because in this paper we show have some predefined latent variable can significantly improve the model. But because we are nowadays we build a much larger general model system. We don't want this encoder to be part of the bottleneck. So we want to have the encoder and general model to train together. Hopefully you have a general system can learn latent variable, also use that to improve the generation qualities. So those kind of the three directions I'm most interested in my features. So yeah, sorry I'm running a little bit late, but thank you. Thank you for your time, also for the questions. And so I will stop here and to see if there are any comments or questions. Thank you. Sorry, is there a message or?
I think some people raise their hand.
Oh,
go ahead.
Go ahead, please.
Yeah, go ahead, Peter.
Yeah, I can hear you.
Oh, I think someone might have raised their hand by mistake and then put it down or something.
Okay.
I have a question about your diffusion model that was the nested diffusion system that you had.
Yeah.
When you're diffusing, are you diffusing directly into pixels, or are you diffusing into VQVA latent space?
It's not VQVA latent space. Some say a clip latent space or MoCo or a Dino latent space.
At the top layer, but what about the one at the bottom?
So it's still the top layer, but we are actually using the patch trick so that you can construct some dense representation from the last layer.
But what about what about theta 1?
Theta 1. Okay, the final one is just standard diffusion model. You can replace it with any. So this is just standard DIT.
But diffusing into RGB space.
For here we are for a comparison, we just use the same setup as our baseline. So it's a VAE latent space.
VAE latent space, okay.
Yes. But because we have different conditions, so the whole the behavior, the property is changing. So that's a key point.
What if you replaced your encoders with VAE latent spaces as well?
Yeah, we actually tried that. So basically, we applet a different choice of this latent space. So basically, what we found actually the generation quality is kind of consistent with the feature quality of the encoder. So you have a better video encoder. You mean quality in terms of say the linear probing accuracy on ImageNet, the classification accuracy. So we already have a worse linear probing accuracy. So we have the consistent observation where basically the clip and the Dino give you the best qualities, and the MAE and the VAE give the worst quality. So that means that's also to emphasize this kind of bidirectional connection between generation quality and the feature learning.
Okay. And what if you just used your VQVAE features instead?
VQVE. We haven't used VQVE here, but I guess still, like I think my impression that VQVE doesn't learn a decent feature as well. So I guess it's maybe worse than Dino and the Clip.
Do you also have an ablation where you study this with REPA? You said you do have that as
yes,
well.
Yeah, we have REPA, comparison with REPA.
So it seems like a large portion of the wins is coming from just using Clip or some additional representation, right?
Yes.
And the nested diffusion process is giving you some amount of improvement, but the improvement's much smaller.
Yeah, so I think the primary message for our model is actually this space matters. So which space you run diffusion. So you are right. So this primary contribution, primary like improvements are coming from we're using some very nice, strong, pre-trained space, pre-trained visual space to do diffusion. Yeah.
So then in the future, is it necessary to have a nested diffusion process, or could you get away with just building really strong visual and representation encoders?
Yes.
And then as long as you have that, that gives you most of the way.
Yeah, that's a very good question. So I think the issue here that, nowadays we try to build much larger generative models with like, more than, 10 billion parameters, but actually the progress of the representation learning community is moving much slower. So whenever this encoder try to be served as a part of the generative system, will quickly become the bottleneck. So actually in the RAPA paper, so what they show actually they improve a lot for if the general model is small. But if you try to make a very strong general model, their improvement basically is very minimal. So that's why I mentioned in the future research direction, it's better to have a system that's jointly learn this encoder and general model together. So you also try, hopefully this kind of encoder part also scalable, can be scalable with your general model together. Otherwise, if you use a frozen pre-training visual encoder, that could quickly become a bottleneck.
Okay, I think that's it.
All right,
Thank you so much.
Right.